Okay guys, welcome back. Jim Malis here. I wanted to do one last video on the dot product and cross product just to kind of tie things up a little bit, or at least clean up on some loose edges. There's nothing wrong with the conclusions that we drew in the first three pieces of literature, in the first three pamphlets, so to speak. When we talked about a look at the dot product, and when we talked about the cross product, and when we talked about more on dot product and cross product, those first three pamphlets, pieces of literature, discussions, there's nothing wrong there. Everything's right. In fact, it's probably a little bit easier to just read the stuff rather than look at the videos. Generally, what I'm seeing, and this is always a learning experience, I'm sure other people are learning this as well that are kind of new to this crisis that we're working through right now, and may it be over soon. Our best hopes on that, and that's what we hope. But I think people that are working with this kind of realize that if you've written at least decent notes, those written notes, if they're pretty decent, are probably as good and very likely better, more time efficient than just about any film that somebody could look at. The film, you can kind of you can talk a little bit more and hopefully foresee some of the difficulties that people might have. The very best is to have strong notes and then do a discussion in person, which is either filmed or not filmed. When it's in person, the person giving the lecture can read the audience, and the audience can read the person giving the lecture. The teacher can read the students, and the students can read the teacher. And the questions that can arise are very good and very useful. And that's a great thing. You can't do that in a film. So you find yourself kind of, I guess, trying to get through this thing. But I think the very best way to get through this stuff is if the notes are pretty strong, and I think my notes are relatively strong. You can, at least I've had students tell me that the notes are fine for them, and they go through it that way. They read the book, they read the notes, and they know how to do the problems because there's a lot of solutions given and there's a lot of lecturing done, and all of that is in just written form. You can kind of go at your own pace, and you're not kind of stuck watching me for 4 hours to maybe get the 1 hour of material that would really interest you, that would really be for your benefit, where somebody else might need 2 hours of it. Somebody might need all 4 hours, But so anyway, that's what it is, you guys. We have what we have, and the people that have helped me have done outstanding work and are continuing to do outstanding work. If you're in the classes that you're taking from me, again, you see all these hard copies online, on Canvas. They're on Canvas. Those of you who are just looking at this and don't have me as a teacher, some of the work that I've done, I put the notes together at the end of the video, and you'll see the notes, and the notes kind of scroll as one big handout. I mean, so these three handouts that I was talking to you about, a look at the dot product, and the other one called the cross product, and the other one called more on dot product and cross product, those three have shown up in all three of the videos that precede this video. We're going to put this fourth piece of literature, this fourth piece of writing, I guess you could say, dot product and cross product. I don't know how well you can see it here. Dot product and cross product, some special case scenarios and summary. So that fourth item will be attached to the other three items that have been bound together. This will also be bound to those three, so we have 4 items bound together. This will be the last one of the 4 that are bound together, and they're all just bound together. It's just one big handout in that regard. So again, I think the notes are just about better than, I've talked to professionals in the field as well, and they've kind of, so at least one person who I regard very highly, a contact person of mine, had said, yeah, I mean, they sort of tended to agree that the notes themselves seem to be better in a sense. So I think so too. I mean, because you can go at your own pace, and it's right in front of you, and it's just more accessible to you. You can page through it, see what you like, see what you don't like, see what you know, see what you don't know, and then go from there. It's a little more awkward if there's a 4-hour video there, guys. And sometimes that's the only way I can make it to make the video somewhat efficient when we're doing something like this. So that's kind of where we are, you guys. So let's kind of tie this thing up And let's see what we can go for. Well, I mean, the good news of all of this was, as I said, the first 3 discussions and the pieces of literature associated with the first 3 discussions are correct. They're correct. And the assumption that we made regarding, remember we'd done a lot of things, but when we had said, okay, if you're going to call forgive me, if you get the erasers, guys. I actually got some good erasers this time, I think. When you got a vector is a sub x I hat plus a sub y j hat plus a sub z k hat. And these are the unit vectors as big as 1 unit, as big as 1. One's the measuring stick. The unit vectors in the x direction, y direction, and z direction respectively, the hat, that's all it means there. And b vector is b sub x I hat plus b sub y j hat plus b sub z k hat. Later on, I'm going to use I and j like this when I'm doing a summation. It's just I like that and j like that. Well, when it's written like that, those can mean the square root of -1, which I'm not going to. We're not talking about that. Or they can be indices of summation. So these are just indices of summation. They are not the same as this. And I'll mention that again when we get to it, guys. But it's not the same thing. These are indices of summation. These right here are what we're talking about right now. Okay. As we discuss further, we drew a conclusion. I did it with, we did a couple things here, and I'm not sure exactly how far I'm going to go with this, but when you did these 2 dot products, we drew a lot of conclusions, right? And the conclusions that we drew that's a conclusion we drew. And then I'm sure you guys, if you looked at the videos when I was doing them, there was an instance where I thought a little bit, and I thought, well, is this always going to hold? I mean, we know it always holds. I mean, we just know just by precedent, by I guess what the great mathematicians have done long before us when they looked at this stuff and say, hey, by the way, we can draw this conclusion. Yeah, okay, great. Did we prove it? Well, we did prove it. We proved it, I didn't give a lot of specifics, but we proved it in a somewhat very general sense. But there were a few special cases that kind of left us perhaps asking some questions. Is this going to hold for every case, every special case? And I kind of just blew it off when I first said it. That's why I wanted to kind of come back today and talk about it a little bit. About it. First of all, there's nothing wrong with what we did in the first 3 videos and in the first 3 discussions and in the first 3 pieces of literature. This is true in all circumstances in 3-dimensional space, in that all-dimensional, in that all-important 3-dimensional space. Okay? So there's a lot that happens. So with a lot we can say. To what degree I'm going to take it, we'll see here. I say here to repeat some earlier work regarding the dot product, and this works for any 2 vectors, A vector and B vector, that are not perpendicular and not collinear. But the perpendicular and collinear cases will be handled shortly, proving indeed that this is always the case. Now, I kind of did it you saw me. I was having some issue. It's always going to be the case, guys. Everywhere, with any two vectors in 3-dimensional space, this is always true. End of the story. Well, we kind of, when we had done this, we did different things. We said different things. You could write it. Let me see exactly how I did it. Yeah, okay. So, a couple different scenarios here. You could kind of write it like this. I think because perhaps it was awkward, perhaps it wasn't. I don't know. You can argue that all day long, I guess. But you could say, you could just as easily have written A vector is A1 I hat plus A2 J hat plus A3 K hat. And then B vector is, let me just see how we wrote it. Right. We could have written a couple, so we could have written it like this. I'm just, again, this is semantics, guys. Is it a big deal? No, not really. Go either way if you want, but just agree to what you're going to be talking about and then go for it. I think when I had first proved it, we'd gone more or less along these lines. We said A vector is equal to A1 I hat plus A2 J hat plus A3 K hat. B vector is B1 I hat plus B2 J hat plus B3 K hat. It's identical to this, guys. It's not different from this. These are the same thing. It's kind of a weird thing. You can prove it using this stuff over here to my right-hand side, but when you give the conclusion, it's almost better. It's more aesthetically pleasing to go here rather than A1 B1 plus A2 B2 plus A3 B3. Either one's fine. But this one's a little more expressive of what's happening here. But it's awkward to do some mathematics with the symbolism here. It's a little more easy to do it with this symbolism, in my opinion. That may not be for everybody. But the bottom line is, we had said a lot of stuff, guys. And, you know, like I said, let me just keep talking a little bit. We had said that, you know, given the nature of the cosine function, A cosine theta is the same as the opposite of A cosine 180 minus theta. Yeah, it's the nature of the business, guys. I mean, if you got something like this, and then you got, you know, let's say this guy's B vector right here, and this guy's A vector right here, and that's theta. Why don't you take A vector and kind of like symmetrically put it over this way. This is all, let's say that's A vector, this is another A vector, I guess you could say. A vector prime, whatever, but it's the same size as A vector. And this angle right here is also theta, just like that one. Then what is this whole thing, guys? Then what is this whole thing from here all the way to that guy? That guy right there is 180. Minus theta. Yeah, this whole thing, yeah, it's as we said, I mean, forgive the repetition, guys, but just in case. This is the 180 minus theta, and you know what? It's got the same exact, I didn't draw this too great, but a little bit more that way. I mean, whatever, you know where I'm coming from, guys. The symmetry of it. So wait a minute. If you do a dot product here, it's going to be as big in terms of magnitude as the dot product here. Notice I ain't moving B vector. I could move B vector and keep A vector kind of stationary, but I'm looking at the angle between them. And basically what we got, guys, is leave B vector alone right there. What are we doing? Okay, the way I drew it, I probably caused you more harm than good here, guys. Make a long story short, this guy right here, there's a dot product. There's a dot product associated with A vector dot B vector, and it's magnitude of A times magnitude of B times the cosine of theta, this acute angle, which is a positive number. So it's AB cosine theta. This one's going to be magnitude of A times magnitude of B, okay, positive number so far, times the cosine of this obtuse angle, which is a negative number. It's the same size cosine in terms of magnitude as the cosine here. Same size, you know, this cosine of that angle and the cosine of this angle are identical in magnitude, but one's negative, one's positive. What does that mean? Well, one of the dot products is going to be AX plus, one of the dot products is going to be AXBX plus AYBY plus AZBZ. The other one is going to be the opposite of that. Negative AXBX plus negative AYBY plus negative AZBZ, if you allow me to say it like that. if they're looking like this, if you're going to put them like this, with some of the stuff that's going on, with the angles associated with it, when you're talking about, you could call that angle, call this angle phi. You know, one is AB cosine theta for a dot product. The other one is the opposite of that. Why is that? Because it's this, cosine phi. And the phi happens to be 180 minus theta. The B could be the same. The B is the same. B didn't change in this case. The A was here or the A was there. Well, it's not really a vector anymore. If you're going to call this a vector, this would have to be a prime vector. I get it. But if you allow me that sort of ambiguity, that sort of non-rigorous treatment of the matter, I think you know where I'm going with this. Well, okay, that means the signs have got to be opposite when this whole thing takes place. Yeah, that's given the nature of the cosine function. Now, we did some stuff. There's a lot that was said. Let me tinker with it. Let me just tinker. This is, guys, we're just confirming stuff we've said in the past. And the stuff I said in the past was true, and I just thought there wasn't a lot of rigor to it because there were some special case scenarios that needed to be looked at, and that's what we're doing right now. We know it's true anyway. We know this is universally true in three-dimensional space for any two vectors. What do you mean? I mean for the vectors, the infinite amount of vectors that I proved it for, and the infinite amount of vectors for which I did not prove it for. When I proved it for, we did that minimization process. We're going to do it again. We know that it was true. It's also going to be true for any two vectors that lie right on top of each other. It's also going to be true for any two vectors that are perpendicular to each other. I didn't really rigorously say that the last time we were together. I don't think I said it at all. I just said, yeah, I even called the instances trivial, which is not true. They're not trivial. Okay. Trivial would be if one of the vectors is the zero vector. That's pretty easy. If one or the other, or both, is the zero vector, yeah, okay, that is triviality. But when they're perpendicular to one another, or when they lie right on top of it, when they're perpendicular to one another, the cosine, it's a 90-degree angle, the cosine of 90 degrees is 0, the dot product better be 0. We got to figure out how that works. And if they lie right on top of each other, the cosine is equal to the cosine of 0, which is 1. And I'm telling you, I don't care what special circumstances I'm talking about, or the other circumstances with which I was somewhat very rigorous. Regardless of the circumstances, I said take it on faith. This is true, and it is true. That was for real. All right, well, let's look at this. Let's see if they're like over from one another. One's here, one's there. Let's see if we can kind of draw a couple conclusions here, you guys. Well, let's say a couple things here, man. I mean, if you're going to bring it, if you got the B vector doing this, and you got the A vector doing this, or doing something else, but not right on top of it and not perpendicular to it, this guy could be going that way too. And we already said about the negative stuff that could happen. We talked about some instances here, what the implication is. We could say if you parameterize, remember we talked about t. Okay, let's put it back in there. T is some multiple of t will give you the size of the projection. So this guy right here, there is, like for right there, on that guy right there, there is B1t, B2t, B3t. Now we've seen all of that before, that argument, one way or the other. For this guy right here. That's this guy. which can be written in a bunch of ways, you know. I mean, but let's leave it at that for right now. So what do we got? Well, we can look at this guy right here, given by all this, parameterized, using t as the parameter. This vector right here in red is the magnitude of a times the cosine of theta. It is that projection. If it is, then it's a times the cosine of theta when you start doing it. Well, what do you mean? Well, sorry guys, I'm kind of putting the carriage in front of the horse a few times here. Yeah, it's exactly what they're saying. And there's a lot that goes on. I mean, you say t squared and again, you can look at this stuff in notes a lot faster than I can write it. And that's what makes the video so long sometimes, guys. In the notes, there should have been a parenthesis, a bracket there, and there wasn't, but it should be. I hope it should be pretty clear from the context, guys. You're seeing it right now. This is a cosine theta. It's the same as this. Now, you know, we need a time out here for a second, guys, the way this thing kind of plays. We got b1 squared, b2 squared, b3 squared equals a cosine theta. Okay, that looks okay. So far, so good. I got to make something clear. If t is a positive number, we're talking about the projection going over toward the right. If t is a negative number, we're talking about the projection going over to the left. If it was like another vector, and that thing would project straight down, and it'd be as big as that guy. So if t is 0, it's straight up. We're not crossing that bridge just yet. We are doing this. If t is a positive number, the projection goes to the right. If t is a negative number, the projection goes to the left. So this does have significance. What happens is some of that information gets lost after you square something. Once you square it, I don't know, the quantity negative 5 squared is 5. I'm sorry, the quantity negative 5 squared is 25. The quantity 5 squared is 25. The quantity negative 5 squared is 25. The quantity 5 squared is 25. I don't know which one was which. I don't know. And the square root of 25 is back to 5. So you got to be careful whenever you're talking about this stuff. You got to kind of know where the origin of everything that was being talked about is to be found regarding something like this. I'll tell you what, maybe the square root of that is the absolute value of t. I don't really know. T could have been negative, so I'm trying to honor that in some regard in the mathematics that I'm doing. Yeah, that's a true story. It's a true story. Tell you what, I mean, yeah, so it's not too bad. Not too bad for us. What we can say is, if that's true, the negativity or positivity, the negative t or the positive t is honored by a cosine theta. Make a long story short, that right there becomes a valid conclusion here. becomes a valid conclusion there, equaling this. Yeah, that cosine theta will make it positive or negative. Or 0. If the theta is 90 degrees, it's 0. Anything other than theta being a 90-degree angle, pi over 2 radians, anything other than that, you're guaranteed an answer that's either positive or negative, and this t will be positive or negative following that. Not an issue. Not an issue. True. We'll tell you what is that? Well, that right there is the magnitude of B. That right there is t. This right there is a cosine theta. Again, let's just make this really clear, guys. If t is greater than 0, if t is greater than 0, that implies the cosine of theta is greater than 0. If t is less than 0, that implies the cosine of theta is less than 0. Okay, that's essentially what I was just talking about, guys. Okay, true. What do you say you multiply by another b? B, this thing right here times another b. If you multiply by b on this side, you're going to multiply by b on this side. Okay, well, that obviously tells us a lot. That obviously tells us a lot. This right there is a vector dot b vector. A vector dot b vector. This is TB squared. Okay, we're not done, but at least we said something. We got to here. Yeah, definitely true. In a sense, if you wanted to find out the size of the parameter and its size, in fact, divide by b squared on each side. A vector dot b vector divided by b squared, magnitude of b squared, divided into the dot product a vector dot b vector, gives you that. Okay. It's of use. It's all of use, guys. We can look at it. So, okay. So as we've said earlier, t is equal to that. The distance between the point A1, A2, A3 and the line, and we have this right here, and we have this particular line for minimum possible value. All of these possible distances. Okay, guys, so basically, what we're looking at is, once we get this, for an infinite number of possible values, I just don't feel comfortable saying that it's true. Actually, I do feel comfortable. It is true everywhere in three-dimensional space for two vectors for which you're getting the dot product, period. We said that a while ago. We said that in the videos earlier. That's true. Let's prove it a bit. This right now, let's not go to them lying right on top of each other, theta equals 0, and let's not look at them being perpendicular to each other, theta equals 90 degrees. Look at every other angle in the universe of angles. We're taking the angles to mean from here to here 180 degrees. Well, why don't you talk about 270 degrees? Because if you go to, or 240 degrees, well, 240 degrees gets over here, and then I can still describe it as an angle less than 180 degrees. So that's not an issue. That's not an issue. So we know this right here, guys. We also know that for these circumstances, for the dot product, look at this. Look at it carefully. Look at this one carefully. That's a perpendicular distance straight down. That perpendicular distance is the minimum distance from the point right here, A1, A2, A3, which is the same as a sub x, a sub y, a sub z, capital A sub x, capital A sub y, capital A sub b. Minimum distance here. So I guess I could use the distance formula and use calculus to get the derivative and set it equal to 0 to get the minimum distance. Once I found the minimum distance, it corresponds to the t that brings the projection of a vector down to here. It corresponds to the t that gives you, well, why write it again? B1t, B2t, B3t. In other words, this guy's components, if you multiply it by, if t was 1, 1, 1, 1, 1, 1, 1, then it'd be this. It'd actually be that vector. But if it's a fraction of that, it proportionately makes it smaller. So there's the point. You're finding this. Well, we did a lot of stuff, guys, last time. Let's do it again. We've seen it, so I don't need to go into the same kind of detail. But I think it's good for us to look at it. The big thing, we got that here. We've got all this. Again, I don't like erasing any of this stuff. That's another advantage, guys. That's an advantage with film. You can always go back, but it's a great advantage with notes. Because with the notes, nothing gets erased. It's all you got to do is page through the notes. That's why I've heard my colleague, so to speak, with whom I was speaking regarding this matter, the person agreed with me. Yeah, it's like the notes have that strength to them, and they're a little more, they're more time efficient. At least I've seen it that way. Perhaps other people don't need to talk as much as I do. So maybe it's something I got to work on as well. But there you go. You got this right here, you guys. So let's see how we're going to look at it. All right, well, we talked about this. We talked about finding the distances. We've been there. We've been there, done that kind of thing. And I'm not going to get into all the subtleties of it once again. Let's just write it down. I could say there is let me see what I can say here, guys. There's an f of t equals, and again, this is, it sure better looks familiar, guys. We did it. We said, let's find the distance. The tip of this guy, which is this right here, to the tip of this guy right here, which is this. Yeah, but this is a fluid situation, guys. That red arrow, I don't really want to do this, so I'm not going to do much of it, but that red arrow can go like that forever and then go this way forever. It just so happens I'm looking at the red arrow, the ideal red arrow. What value of t will give me that ideal red arrow where it's perpendicular? But this guy right here is a parametric equation of a line in three-dimensional space. It's a parametric equation of a line in three-dimensional space that'll give you the equation of a line in three-dimensional space. So let's look at this. All right, it sure, yeah, if it looks familiar, yeah, it should. We've done it. You've seen it in the notes at the very least. We got this. Yeah, we've been there. Well, look, we said there's a number of awkward scenarios, at least one awkward scenario that could take place if you want to just stay with this. I tell you what, to find a minimum value for this function, why don't you just find the minimum value of, rather than capital F of t, find the minimum value for small f of t, where small f of t is giving you a function that's complicated enough as is. Find the minimum value of what's underneath the radical. The radical cannot get very big if what's underneath it is very small. That radical, what's underneath the radical, I mean, that function, capital F of t, cannot have a very big value if what's underneath the radical is a small number. Capital F of t is driven by what's underneath it. Capital F of t is driven by what's underneath it. If that's the case, make your life easy rather than throwing square roots and all this other stuff there. We can go the other way too, but we're kind of introducing some challenges. I'm sure we could circumvent the challenges. You saw me kind of go there the last time, how well I circumvented it. I just kind of said, well, let's just leave it alone. That's how I handle it. So let me handle it that way again right now. Let's leave it alone. Go here. Take what's underneath the radical, and that's going to drive how big or how small the distance is. It's a big determination of what's going on. So if that's the case, we're essentially saying df of t dt, set it equal to 0. df of t dt set equal to 0 is going to be indicative of the value of t, the value of the parameter t that'll make b1t, b2t, b3t, will make that line segment the projection, the perpendicular projection onto b vector. It'll give you the length of that vector that is the perpendicular projection of a vector onto b vector. That's always been the argument. It's the value needed for a minimum. True. By the chain rule and the sum rule, you've got this. And you've got this. Here we go. By the sum rule and by the chain rule, let's go chain rule here. Derivative of this is going to be 2 times this quantity to the 1 times the derivative of this quantity with respect to t, which is b1. So it's 2b1. Got to be careful. Same argument's going to take place here and going to take place here. Obviously, the symbols are a little bit different. And obviously, I don't know what I'm doing. Hold on a second here, guys. Whenever I run out of room like that with the large writing that I do, it sometimes does not bode very well. Let's see what happens here. Okay, let's try it again. Here we go. Chain rule. We end up getting to the end of the song and dance. You end up getting plus okay. Yeah, there's a good amount there, guys. But let's see. Let's just kind of, I always need more room, or I always need to write smaller. I'd rather write large enough that things are pretty clear for everybody. Okay, you're doing this. Setting that equal to 0. Doesn't have to be set equal to 0. This is what the function is. It's only at its minimum when you do set it equal to 0. So it doesn't have to be set equal to 0. It's whatever. These are an infinite number, probably an infinite number of values here. Indeed, there are an infinite number of values, for sure. So what? I only care about the one value of t that'll make it equal to 0. So that's really the big thing. That's all that right there, guys. Well, the rest is do some mathematics. Okay, and let's see what we can say about that. You tinker with it a little bit. It says a bunch of things. Let me write down a couple things here really quickly, you guys. Let me just stop this thing for 1 second. I'm going to come right back, okay? Okay, guys. So I just want to erase that a little bit, get situated a little bit with this thing. So what's going on here? I mean, when we had looked at it, you saw what was written up there earlier. Now what can you do? What do you see possible? What do you see impossible? Well, I'll tell you what. Without worrying too much about this, we got this, the FDT, and what we had was the 2BI, all those things there. I tell you what, there was a 2 going on everywhere, guys, so why don't you pull the 2 going on everywhere that was there. In addition to that, you were basically, the way it was looking, now let's I don't know, I think it's important to kind of look at it. We were roughly in this vicinity last time we were together, guys. Before I cut out and came back, guys. I mean, we could say, we were saying something like this, B1, and we were playing all these games with this thing. I should have a little bit more room now. 2B2. B3, there it is. Well, yeah, okay, we've already kind of said this. Why don't you take a 2 out from all of those? Why don't you take a 2 out of there from all of those? From all of these, take a 2 out of there. Go B1, B1, T. That's B1 squared T. B2, B2, T. B3, B3, T. Wait a minute. What's going on here? You already took the 2 out of everybody. The 2's already out of there. B1, B1, T. B2, B2, T. B3, B3, T. What does that mean? It means this. It means that right there. Times T. Minus, what's going on here? B1A1 minus B1A1 minus B2A2 minus B3A3. Minus all those, huh? That's the same as minus the sum A1B1 plus A2B2 plus A3B3. Absolutely. Great. Again, what does that mean? Oh yeah, I mean at the end of the day, you guys, remember, you're setting all of this equal to 0. Great. Tell you what I'm going to do. If it's all set equal to 0, let's stay here. If it's set equal to 0, we already took care of what we already took care of dft dt. We already took care of dft dt. If all this mess, and again, be careful, it's all of it multiplied by 2. Very important. If you divide this side by 2 and you divide 0 by 2, you get some interesting conclusions. So okay, let me erase some of this stuff, guys. I think you can always come back. That's maybe one thing I can appeal to people to, and saying, okay, you've got all this in the notes, come back to it in reference to what I'm trying to say. Let's see what is going on here. Let's see if this is hopefully a good move for us. What's going on here is, divided by 2, you did the whole thing here, and you end up getting B1 squared, B2 squared, B3 squared, times T. Forgive me. Minus the sum equals 0. Equals 0. Great. Add minus all this, add positive all this on each side. I'll put the T in front. You're adding this amount on each side. It was being subtracted here. So add the opposite. This is like minus this is plus the opposite of all this. Well, add the opposite of the opposite. Add a positive all this on each side. It's gone, leaving you just with this. And the positive of this on all sides is this. True. Wait a minute. We were drawing certain conclusions here, but let's draw the conclusions we want to draw, I guess you could say. Right here, multiply by b, forgive me, but multiply by b squared again. That's a vector dot b vector. Wait a minute. This squared plus this squared plus this squared is the magnitude of b vector squared. Is the magnitude of b vector squared. I tinkered with this stuff earlier. Who knows? Maybe I erased the wrong stuff. I mean, not really. They're all equal. They all kind of derive from the formulas as they derive, and you can give different expressions for the mathematics. I chose this expression. It wasn't too bad. If I multiply by the magnitude of, this means magnitude of b. I don't see a vector symbol here. This is magnitude of b squared. The magnitude of b squared multiplied on each side. Multiply by the magnitude of b squared multiplied by the magnitude of b squared on each side here, you get this. That's this guy. Wait a minute. I've been drawing these conclusions already. A vector dot b vector is a1 b1 plus a2 b2 plus a3 b3. Yeah. And remember, the A1 is AX, the A2 is AY, the A3 is AZ. The B1, B2, B3 is BX, BY, BZ, respectively. To make the long story short, I'm going to start erasing a little bit more, guys. I'm sorry, but we got this. And that's where we were coming from. That's how we played that game last time. Absolutely. And that holds for an infinite, and that holds for sure, ladies and gentlemen, for an infinite number of vectors where the vectors are at angles with one another, at an angle with one another of anything other than a 0 degree angle, other than they don't lie on one another and they're not at a 90 degree angle from one another. I haven't proved those two scenarios yet. It's going to be the exact same conclusion. It's going to be the exact same conclusion. But this holds for an infinite number of vectors. This holds for an infinite number of vectors, you guys. And how clear this is, guys. I'm always a little apprehensive. I don't know how good the video quality is going to be on that, but here it is. Yeah, it's a little easier. Okay. Absolutely. Well, yeah, I proved it for a massive number, for an infinite number of scenarios. As long as theta is not equal to 0 and as long as theta is not equal to 90 degrees. Yeah, we don't care if theta is equal to 0 and we don't care if theta is equal to 90 degrees. It works there also. I just said it a while ago, many times. I'll say it again. It works for all vectors. Any two vectors in three-dimensional space, their dot product, regardless of their angle, without exception, their dot product is that. I'm going to show that in the two special cases, which rounds this off and gives us that conclusion. Very important conclusion. Okay. All right, there it is. You'll see it again. I mean, when we look at it, and we say, and the notes have it there. I go into it a little bit. What I did was, now to complete the proof, guys, let us look at the fact that also there's an A scenario and a B scenario. A scenario, if A vector and B vector are perpendicular, if A vector and B vector are perpendicular to each other, not only are all those infinite things, not only are all those infinite scenarios with vectors true, giving you that, not only is it true that this is the scenario of the dot product, it's also true if A and B are perpendicular to each other. It's also true if A and B are at 0 degree angle with one another, they lie on top of each other. There's an A scenario, A vector and B vector perpendicular, and it's still going to be this. And there's a B scenario, A vector and B vector are collinear, and it's still going to be this. Those two special case scenarios that were kind of bothering me the last time I did the video, so I need to kind of talk to you about it a little bit if I could. Well, yeah, you're not going to. Let's look at the B scenario first. Let me look at if they're both collinear first. And then let me go to, saying, Malas, why didn't you, hey, Jim, why didn't you just write the A and B and kind of like call one of them A, call one of them B, but just do the order reverse of what you're calling what? I wrote it like this. Let's write it like this. Let's do the B scenario first, guys. Let's look if they are collinear. Can you talk about it? Can you draw a conclusion on it? All right, so let's see what we can say. We're saying we're going to get the same scenario here. Let me... All right, well, we said some stuff. In fact, that thing I said holds, believe it or not, the thing we were talking about. When we talked about, T, forgive me. TB squared equals A vector dot B vector, how the whole thing's going to play out. I mean, the whole, the TB squared Why did I keep writing the vector there when it's a magnitude? I don't know, guys, but there it is. Okay. We got magnitude of A times magnitude of B times cosine of the angle between them. If it were a 90-degree angle, the t is 0. The projection right down onto it is 0. If the projection right down onto it is 0, magnitude of A times the magnitude of B. Wow, those are magnitudes. We're going to say neither one of those is a 0 vector. Those are trivial cases. We don't care. That stuff's easy. A vector, B vector are vectors with magnitudes that are non-zero. Each one has a non-zero magnitude associated with, each vector has a non-zero magnitude. AB, yeah, fine, big number. Apparently, yeah, let's say it's a really big number. Yeah, the cosine of 90 degrees is 0. It's done. And this t does it also. Yeah, that would be for a 90-degree angle. That would hold. Here's where it gets messy. Is it indeed guaranteed that AX, BX, and AY, BY, and AZ, BZ? That's a lot of stuff I'm throwing in. That's a lot. There's a lot of products here, a lot of sums, and you're telling me that? Yeah, I know it's 0 here if they're perpendicular. I know that. Man, to me, this is the problem I was having last time. By the way, this is true when they're perpendicular, but that's not obvious. This is obvious. T is 0. Sure, you're here, you're here. It goes, here's your projection. That's got to be t equals 0. For T, B1, T, B2, T, B3. Yes, absolutely. Yeah, that's got to be 0. I get that. Great. That doesn't tell me if this is B. Let's go up here. If this is B and that's A, if you get the components of this guy and get the components of this guy and link them up like this, that's equal to 0. That's not obvious. I mean, this is. This works. You see me work it, and that'll work for a lot of stuff. And this works too. I mean, I just told you, you can make t equal to 0. You could make t equal to 0, and and we already know the cosine of 90 degrees is 0. 0 times, I don't care if it's a billion. 0 times a billion is 0. If that's 0, 0 times this, 20 billion, let's say. 0 times 20 billion is 0. 50 billion times 0 is 0. Yeah, okay, we get all that. That ain't obvious when they're perpendicular. That was my issue. And that's kind of a huge basis of the discussion today, actually, why I wanted to talk about that. If they're perpendicular. If they are if this is B vector and A vector lies right on it, then same scenario. Yeah, okay, what, well, A vector would have to be equal to some parameter t times B vector. True. Therefore, you could play a whole bunch of things here, man. You could say, okay, if that's true, then A vector dot B vector is magnitude of A times magnitude of B times the cosine of theta. Well, yeah, these are two different scenarios, guys. Two different scenarios. We know that. We know this. Yeah, the cosine of 0, this is a 0 degree angle. This right here was 90. This guy right here earlier with perpendicular, that's 90 degrees. Yeah, I know, cosine of 90 is 0. This is theta equals 0. The cosine of 0 is 1. A vector dot B vector is this. True? Yeah, it is. That's true. A vector dot B vector is the magnitude of A times the magnitude of B. Yeah. Yeah, I don't know, man. That's true. That is true. Nobody's debating that. I want to, for the sake of argument, I want to debate this. That's not obvious. You know, this wasn't obvious with the 90-degree scenario, but we're hoping it is, because that's the way we defined that's the way we talked about A vector dot B vector. We said this: if you do the dot product of two vectors perpendicular to each other, that right there, that whole mess, beautifully has to be 0. Yeah, that's very important in our future conclusions when we work on the cross product. Or in our past conclusions, so to speak, because we already did film earlier on, hey, the cross product. How do you determine orthogonality, perpendicularity? How do you determine if they're orthogonal to each other? The dot product's got to be 0. The dot product defined like this. Wow, that's not obvious. This other stuff was obvious, coming out to 0. I got no problem with this. We got no problem with this, guys. That whole mess, does it hold like that? Same thing here. I don't think any of us got a problem with this. Coming from this guy. Yeah, if they're right on top of each other, what's the projection of A vector onto B vector? If they're right on top of each other, it's right on it. A vector doesn't lose any size in projecting itself down onto B vector. It's already on B vector. This A cosine theta is the projection is A cosine theta. Yeah, I know. A cosine theta is A's projection, but the cosine of 0 is 1. A cosine theta is A. A and B, bam. Magnitude of A is the size of the projection on B vector. Why? Because it's already lying on B vector. Yeah, there's no problem here, guys. The challenge is this. Is that true? Well, I already in past videos assumed that was true for everything. For all vectors in three-dimensional space, I assumed that it was true. You name any two vectors in three-dimensional space that you wish. Any two vectors in three-dimensional space that you wish to discuss, their dot product is given by this. This thing right here. So if they're right on top of each other, A times B is equal to AX BX plus AY BY plus AZ BZ. If they are perpendicular to each other, giving you 0. Well, there it was AB, right on top of each other, and it was AX BX plus AY BY plus AZ BZ. Here, perpendicular at 0, but it's still AX BX, AY BY, AZ BZ, all of that added together. That's the challenge. Those two we got to find and make it work. Okay. Let's start with the collinear case and take it from there. I cannot emphasize enough in this particular problem that that's true. If they are collinear, ladies and gentlemen, A vector equals T B vector. And they are completely, let me pull something from triangles, but let's work with triangles in three-dimensional space, in a sense. They are completely similar vectors. One is just a multiple of the other. Now, if they're the same size vector, A vector equals T B vector. A vector equals T B vector. If T is equal to 1, what happens? A vector equals B vector. They're the same size if T equals 1. If T equals a half, it's half as big. A vector is half as big. If T equals 1 million. If t equals 1,000,000, A vector is 1,000,000 times the magnitude of B vector. It lies on B vector, but it's 1,000,000 times longer. But it lies on the line determined by B vector. So on and so forth. Let's talk. And then we come right back to this, guys. So wish I didn't have to erase it, but like I said, once we've seen it already, we've got the two problems in front of us. Let's solve them one by one then. Let's go there. They're collinear, guys. We said a lot. I mean, we've said a lot. It's already there. So let me not beat this up too badly, I guess you could say. A lot of ways you can go here, I guess you could say. You could say theta could be 0, or theta could be 180 degrees going in the exact opposite direction. The cosine of 0 is 1. The cosine of 180 is -1. But they both lie on the same exact line determined by B vector, or determined by A vector. I mean, they're both collinear. The cosine of 180 degrees is -1. The cosine of 0 is +1. So we've got a lot of situations here that could happen. So we got 180 and we got 0. So similar situation. Here's B vector. Here's A vector. They're not the same size. I made them look like they're the same size, but they're not. Theta could be equal to that too. Okay? All right, I can always do this stuff faster, guys. I'm never very comfortable doing it. I feel like I could lose people a lot easier, so I don't know. Going too slow, you can lose people sometimes too. So I don't know what to tell you guys. It's kind of it's a very awkward scenario to be in sometimes. Look, let's come back to something very important, and we'll say that A vector. Now look, if t is a number, and it's a trivial case now. If t is equal to 0, then the A vector is 0 size. That's a trivial case. That's easy. That's easy. If A vector is 0 size. If A vector is 0 size, then AX is 0 size, AY is 0 size, AZ is 0 size, and those 0 times something plus 0 times something, each one of these is 0. 0 times something, 0 times something, 0 times something, it's 0. That's easy. We're not going in the trivial cases, guys. Too easy. We're going to say that if you wanted to talk about A vector, t times B vector would tell you if t is a number greater than 0, A vector and B vector are not only collinear, but they are parallel rather than anti-parallel. They're both on the same line, regardless of the situation. If it's 180 degrees or 0 degrees. It's a 0 degree angle if t is positive. If t is negative, it's a 180 degree angle. It's the only difference. When you look at this, you could say that the magnitude, the absolute value of A vector, the absolute value of the magnitude, it's kind of awkward. The magnitude's always a positive number anyway, right? But let's just, I don't know how to say this. Let me just say that, though it's maybe a bit redundant. A is the magnitude. Let's talk about an absolute value here. Well, it's already going to be positive, so. And if you took A over B and you multiplied it by B, what's going on here? It's not the best way. I'm already sort of regretting the way I'm writing it, but you're looking at a situation. Let me maybe write it differently. Plus or minus here, plus or minus here. Yeah, I mean, you could say that. I can debate aesthetically how it works for us aesthetically here, I guess, guys. But for now, let's write it like that. The big thing is this. T is equal to, solve for T. That's A vector over B vector. A vector over B vector, which is the same as the ratio of components. And here, the sign matters. AX does not have to be a positive number. AX could be a negative number. BX could be a positive number, it could be a negative number. AY, the whole thing. AX over BX. AY over BY. AZ when vectors are collinear, that is true. All of that is true. We know enough to say that A vector dot B vector equals AB cosine 0 degrees is equal to AB. You're done. We got A vector dot B vector equals AB cosine 180 degrees, and that's equal to negative AB, where A and B are both positive. Here, these aren't guaranteed to both be positive. That could be a negative number. That could be negative 5, that could be positive 10. In which case, this could be negative 10 and this could be positive 20. This could be negative 30 and this could be positive 60. And the ratio is negative 1/2. So we know that. We've said that. All right. Let's get ourselves out of the woods on this for either scenario here. We drew the conclusion. Again, of course, I erased it, but you've seen it already in at least 2 videos already. Maybe 3, but at least 2. We have seen the validity, and I've discussed it, TB squared, which is TB times B. That's TB squared. TB squared is TB times B. True. What does that mean? Well, let's keep talking, I guess. That means TB squared, right, we already said that, is, what's B squared, guys? It's B sub x squared plus B sub y squared plus B sub z squared. Absolutely. Yes, that's true. I mean, the math, we've seen the math on that. We're fine. Okay, let's talk some more. Take this guy and let me bring the t inside and break this thing up a little bit. Bring the t inside. I'm going to bring the t inside here, the t inside here, the t inside here, and then I'm going to break up the b squared into here and here. You'll see in a second. The t went over here. I'm going to break up the by squared into tby, and into T. Okay, you'll see. This is easier done than me talking too much, I think. Yes, true. Really? Yeah. Take a close look at that, guys. Sometimes the stuff is written just fine, guys, and I try to get too artistic about the whole thing. All right, you got this right here. True. I got to talk to you. They're all equal to T. Every one of these ratios. Take this ratio and multiply it by BX, and you get is AX. Take this ratio, multiply it by BY over here. AY, sorry. Take this ratio, multiply it by BZ on each side. Well, on each side, I don't want to mess with these too much. You can get all kinds of conclusions that can maybe confuse you more than they help you. Just take a snapshot of this guy and deal with these two guys. Deal with this and deal with that. When you're done with that, deal with this again and deal with that one. When you're done with that, deal with this again and deal with this other one. Multiply by BZ on each side. So what do you got? Okay, that's pretty important. TBX, ladies and gentlemen, is right here. TBY is right here. And TBZ is right here. Yep. And TBX is AX. TBY is AY, and TBZ is AZ. Yeah, that's huge. TBX is AX, TBY is AY, TBZ is AZ. A vector dot B vector equals AX BX plus AY BY plus AZ BZ when theta equals 0 or when theta equals 180 degrees. It also worked in an infinite number of other circumstances. I mean, even this is infinite number of circumstances because the size of the vectors could be different. That's true. So I could create the diversity there that could be infinite. But at least for angle diversity, there's 0 degree angle and 180 degree angle, and if they are collinear in both cases, this holds. This, you saw it. I mean, this held from way back. And we got that. This we said because they're collinear, we solved for AX, we solved for AY, we solved for AZ, and AX was TBX, AY was TBY, AZ was TBZ. Whoa, TBX, TBY, TBZ, AX. I'm sorry, AX, AY, AZ, right on the mark. It works. It works. What about the 90 degree angle? Let's say, so it accounts for the sine. It's already accounted. The ratio accounts for the sine because that could be any real number. The 0 we regarded as trivial. But everything, put it in there. It can be any real number. T could be any real number. And we talk about it, I went into a little more detail. You can read the stuff I got there, guys. If they are perpendicular, we're going to utilize the Pythagorean theorem to kind of get there. I mean, yeah, we knew it was easy if it's perpendicular. How hard can the perpendicular case be? Give me the dot product of two vectors that are perpendicular to one. They're non-trivial vectors. They're both non-zero vectors in terms of magnitude, each of them. Non-zero vectors in terms of magnitude. They're perpendicular to one another. What's the dot product of two vectors that are perpendicular to one another? Yeah, it's 0. What's the projection of B vector onto A vector if B vector is perpendicular to A vector? It projects right down onto A vector at 0. It leaves no shadow. It's 0. So the magnitude of one times the other, the magnitude of the projection is 0 times, I don't care how big the other one is, 0 times anything is 0. Yeah, we know that. The problem is, what about the components of A? What about the components of B? Is it obvious that AX BX plus AY BY plus AZ BZ, is it 0 consistent with what we've done all this time? It's worked all the way up to this point on everything. Does it work for the 90-degree angle case? So let's look at that. That's what I just thought. I just thought that was important, guys. Like I said, we never doubted it. We knew it would work. We knew we could sit down and do it. I debated with myself whether or not to go through this with you guys. Why not? Why not look at it? Okay. I knew it would work. We kind of threw it by the wayside. We say, hey, by the way, it's going to work in every single circumstance, and it really does. And then we were able to use that, exploit that reality of the dot product to really derive in some pretty interesting ways to derive the cross product. And again, Munham and Foulis and their brilliant work on the cross product, like I said, I wanted, and there's nothing wrong with what they did. What they did is absolutely brilliant, but I wanted to actually kind of explicitly talk about the size of the cross product. And could we get vectors, there's the size of the cross product, let's get a relationship that tells us in terms of components that is consistent. We look at the components and we find out, hey, wow, magnitude of A times magnitude of B times the sine of theta is the magnitude of the cross product. Can we actually derive that? Yeah, we actually found that. We took a couple guesses in the way that I wanted to look at it, which I'm sure other people looked at it as well long before I did, but in the way I proposed initially, okay, you got the dot product, take a couple guesses and find out which vector is the right vector. As far as there's going to be two vectors that are orthogonal to those two vectors, and they both have that size of AB sine theta, but which one's right-handed? Only one of them's right-handed. It's always right-handed, and the other one's always left-handed. So we went there. None of that would have worked if we couldn't prove this for everything. A vector dot B vector equals AX BX plus AY BY plus AZ BZ. Okay. So we looked at this. Let's just get rid of it. We already said a lot about it, so let me not rewrite a lot of the stuff that we said. Let's look at it and see how we getting, the goal is it always going to be the case giving us the conclusion consistent with what we always thought, and we were right to think so, regarding the dot product. What's the dot product? What's the general way of saying it? Well, there's two ways of saying it. One's a lot more elegant, for lack of a better word, than the other, I guess you could say. Okay. Yeah, we're hoping. It's a 90-degree angle. We do know this, and it's believable. We already know A vector dot B vector is AB cosine theta. Yeah, that's the definition. can you say this always? Well, so far so good. Yeah, you can say it always. You're going to see you can say it always. Yeah, it's a tough one. Yeah, and even if they're at 90-degree angle, is it going to be 0? Yeah, this is 0. This being 0 is obvious. The projection onto it is 0 size. The shadow of A onto B is 0 big. 0 times the magnitude of B is 0. I get that. That's not a problem. Is it equal to this, though? Can this rather elaborate process, is it always ax bx plus ay by plus az bz equal to 0 if it's a 90-degree angle? Let me give you 2 looks here. It's not really going to be too much of an issue. Let's look at A vector looking like this, and B vector looking like that. And you can imply here, you guys, if you took A vector and B vector, if you added the 2 by the parallelogram method, that's A vector plus B vector. You know, that's the same as picking up A vector and putting it right here, guys. Maybe that's somewhat easier to look at. Either way, guys, that's a 90-degree angle right there. We're not debating that. Okay. You'll see what I'm doing here in a second. So, okay. I mean, that's enough of the math, I guess you could say, to kind of look at it and say, okay, well, let me put A vector right here, and put B vector right here. This is A vector plus B vector. Okay. Got another one for you. If you go A vector minus B vector, this is A vector minus B vector, believe it or not. And the other one was, like I said, going this way. They're the same size. The diagonals of that rectangle are congruent. The 2 diagonals of that rectangle are congruent. We could prove that in a bunch of ways. The side angle side postulate is absolutely the way to go, probably. Side, side, side. I mean, well, not side, 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 but side angle side would probably be the way to go on that. They are the hypotenuse in both cases, guys. Believe it or not. The magnitude of A vector plus B vector and the magnitude of A vector minus B vector, they're both the hypotenuse. They're both of equal magnitude. Well, that's kind of weird to look at. It doesn't look like it. I mean, one's plus, one's minus. What's the size of A vector, B vector? It's the same size as A vector minus B vector. Yeah. Look at it. I mean, we can prove it. Got to remember, this guy was coming across. I mean, I can draw a rectangle, and all the symmetry that's present, the diagonals of the rectangle, are congruent. There's a part 1 and there's a part 2 scenario to this thing. Part 1 scenario is this guy. So these guys mutually imply each other is what happens here. So there it is. Let me just debate with myself how I'm going to do this. All right, let's go with this guy. I'll eventually See, I'm eventually going to have to erase, I think, somewhere, guys. I don't see me having a lot of room, but let me see what I can do. Let's go with this scenario. This is the part, this is kind of the part one scenario, so to speak. Let's say something that's not a whole lot profound, but let's say it anyway. The sum of A vector plus B vector, the sum of that one big vector called A vector plus B vector, is the sum of A vector by itself plus the sum of B vector by itself. Yeah, okay, well, I didn't say a whole lot. I mean, this thing, looking at it, it's not too much to say. Got another thing to say. The magnitude of the sum, ladies and gentlemen, the magnitude of the sum squared is equal to the magnitude of one of the legs squared plus the magnitude of the other leg squared. Is that true? Absolutely, it's true. Why is it true? Because the magnitude of this vector is C, the magnitude of this vector is A, the magnitude of that vector is B, and C squared equals A squared plus B squared for any right triangle. They are perpendicular to each other. For any right triangle, the magnitude of the hypotenuse, the magnitude of the sum of the two vectors, A vector plus B vector, is equal to C vector. This is A vector, this is B vector. The magnitude of C vector is C, the magnitude of A vector is A, the magnitude of A vector is B. Plain and simple, the magnitude of this vector is the hypotenuse. We'll call it C for magnitude C. The magnitude of this vector is magnitude A, the magnitude of this vector is magnitude B. C squared equals A squared plus B squared. What is going on here? This is pretty important stuff. It's a pretty important move we made. If you square the magnitude, guys, isn't squaring the magnitude. Now we got to be extremely careful. Is A vector plus B vector dotted with A vector plus B vector, is that the same as, now you got it, this gets interesting. The magnitude of A vector squared is AX squared plus AY squared plus AZ squared. That's the magnitude of A vector squared. The magnitude of B vector squared is BX squared plus BY squared plus BZ squared. That's a big move you got to make. We also know, yeah, that's true. The magnitude of A squared is AX squared plus AY squared plus AZ squared. From another application of the Pythagorean theorem, likewise, the magnitude of B squared is BX squared plus BY squared plus BZ squared. The magnitude of A vector squared, magnitude of B vector squared. Yeah. What is the dot product of a vector with itself? Well, that's pretty interesting. Let's be careful with that. Let's be really careful with that. Excuse me, guys. I got to make sure I got enough battery life here. All right, should be okay for a while. Now we got to be careful. Yeah, it's important that we actually discovered earlier, verified, discovered is probably a better word. We discovered that the verification is okay. We discovered a very good verification. We discovered the consistency, that A vector dot B vector. That A vector dot B vector is AXBX plus AYBY plus AZBZ if A vector and B vector are collinear. These guys are definitely collinear. Why are they collinear? Because they're one and the same vector. One vector lies on top of the other vector because they're identical vectors. Extreme caution here. What does that mean? That means, okay, now I want to be, I just hope I got enough room here, guys. You guys can read me okay here. Eventually got to erase some stuff, I think, too, guys, but okay. Here we go. The dot product of these two vectors we have shown to be the x component multiplied together, the y components multiplied together, and the z component multiplied together. Okay, let's be careful. This guy right here is ax plus bx times I hat. It's also, or more parts of it are the following. AY plus BY times J hat. It's also constructed by keeping in mind AZ plus BZ dotted with the exact same thing. Let's see how I'm going to do this, guys. I'm kind of I'll write this again, it looks like, but let me just stay with it. Let me kind of talk to you. Stuff is easier, as you hear me say so often, stuff's sometimes easier done than said. Okay, well, I officially ran out of room there, guys. I got this guy. Let's talk, and we'll figure out how we're going to write it. I'm probably going to have to write it. I almost for sure got to write this again. You see what we're trying to confirm? You see a lot of stuff here, guys. I don't need to deliver the speech again if I've written it down a bunch of times. You guys know where I'm going. I'm going to get this second scenario in a second, just to kind of verify it. So you know it's not some kind of thing we're making up here, guys. It has universal validity, so to speak. What is going on here, guys? The sum of A vector and B vector is a vector. The sum of A vector and B vector is the same vector, and it is a vector. We said when vectors are collinear with one another, the dot product does indeed work the way we always thought it worked and the way we're going to prove that it always works for all scenarios, and we're almost there. The dot product, we know for sure, we just proved it, for collinear cases, when vectors are parallel to one another or anti-parallel to one another, A vector dot B vector equals AXBX plus AYBY plus AZBZ. True. The vector, A vector plus the sum, A vector plus B vector is one vector. We'll call it the sum of A vector and B vector. What is the x component of A vector and B vector? It's the sum of the x components of A vector and B vector. That's the x component. What's the y component of the sum A vector plus B vector? It's the sum of the y components of A vector and B vector. What is the z component of A vector plus B vector? It is the sum of the z components of A vector and B vector. And that's the same thing done right here. And that is equal to that's all this right here, guys. That's all this right here. And that's equal to this. I'm sorry I ran out of room, so let me go over here. And what is that? That's this. Forgive me, guys, it's kind of all over the place here, but I guess that's one advantage to the film, I guess. You can go back. So what are we saying here, guys? Yeah, we're saying this. We're saying that this guy right here is indeed this guy. And that guy right there is indeed that guy. Yellow, what's circled in yellow equals what's circled in green. What's circled in yellow equals what's circled in green. Right below it, what's circled in yellow equals what's circled in green. All right. Now, yeah, okay. Now what are you going to do? Well, guys, look, this I cannot emphasize how important this is in the process. That thing right there and all of this, same thing. Yeah, we proved it. That's why I wanted to go we looked at this kind of backwards. I said, hey, let's look at the collinear situation first. We already found out that the collinear, when two vectors are collinear, A vector dot B vector equals AX BX plus AY BY plus AZ BZ. What does that mean? Well, that means these two vectors are collinear. You're gonna link this guy's your AX, this guy's your BX, this guy's your AY, this guy's your BY, this guy's your AZ, this guy's your BZ. What are we talking about? I already got those. I'm just saying call this guy mega A sub X, call that mega A sub Y, mega A sub Z, and mega A sub X, mega A sub Y, mega A sub Z. When you do the dot products, this guy and this guy are multiplied together. This guy and this guy are multiplied together. This guy and this guy are multiplied together. We proved that earlier. We were pretty slick about it. We proved it earlier. Now we can use it. Now we can use it. So what's going on? Well, let's go. Let's get this. This guy, the quantity AX, BX. Okay, so here's what goes on, guys. You end up getting AX, BX, I hat, dot with AX, BX, I hat. AX, the sum AX, BX, the sum AX, BX, I hat, dotted with the sum AX, BX, I hat is this. AY, BY, J hat, dotted with AY, BY, J hat. AZ, BZ, or AZ plus BZ, K hat, dotted with AZ plus BZ, k hat. Okay, what happened here? The quantity ax bx I hat dotted with the quantity ax bx I hat is the quantity ax plus bx squared. The quantity ay by j hat dotted with the quantity ay by j hat is the quantity ay by squared. The quantity az bz k hat dotted with the quantity az bz k hat is the quantity az plus bz. I'm sorry, you always mess it up, guys. The quantity az plus bz k hat dotted with the quantity az plus bz k hat is the quantity az plus bz squared. And we're claiming, man, we made and that equals, that's this. We got all this. Now I'm going a little bit, we got all this. And that's equal to that. That's equal to this. Let's see what happens. Okay, be my guest. Square this, you get the quantity. Well, look, I'll tell you what, maybe it's probably a little easier done than said. So let me not talk too much. Wow, that ax bx, huh? We definitely need to see that. We got okay. Okay. You guys know where I'm going. You probably know where I'm going better than I do actually right now. Let me see what I can say here. Okay. So we were here. All right, guys. Where am I going? Where am I trying to go here? Well, I'm just saying they're equal. We proved they're equal. All right, let me subtract. You know where I'm going, guys. You know where I'm going by now. Let me subtract ax squared on each side. Let me subtract ax squared on each side. Let me subtract ay squared on each side. Let me subtract az squared on each side. So let me write it. Ax squared. I subtracted the sum ax squared plus ay squared plus az squared. Well, I subtracted the sum ax squared plus ay squared plus az squared on each side. Well, yeah, here's the sum ax squared plus ay squared plus az squared on each side. Then I'm going to subtract bx squared on each side. I'm going to subtract by squared on each side. And I'm going to subtract bz squared on each side. They're all gone. That's 0. almost everybody's gone here except for 2AXBX, 2AYBY, and 2AZBZ. I add those together and they equal 0. You definitely know where I'm going right now. Absolutely. What's left, ladies and gentlemen? 2AXBX, 2AXBX, 2AYBY, 2AZBZ. We just said everybody got lost on the left. Look at it. Everybody got lost on the right-hand side. Everybody got lost on the right-hand side. You got this. I get it. About 5 minutes ago, you saw the conclusion. Let me just, from the standpoint of the aesthetics, I guess. Divide by 0 on each side. I'm sorry, forgive me. Divide by 0? No, I'm not making up my own math, guys. Forgive me, I'm wrong on that. Divide by 2 on each side. Divide the 0 by 2. Divide each side by 2. All of this multiplied by 2 divided by 2 is just all of this. 0 divided by 2 is 0. Divide by 2 on each side. AXBX, AYBY, AZBZ equals 0, always. Good. That means A vector dot B vector, the way we've defined it in the past, has validity. AB cosine of theta, where theta is a 90-degree angle. The cosine of 90 degrees is 0. 0 times AB is 0. Yeah? I got news for you. AXBX plus AYBY plus AZBZ is also equal to 0. It holds there also. So what I threw by you guys in earlier videos isn't as trivial as I was letting on. I mean, I guess I could say I misjudged it as well. It's there. There's no problem. We came up with the right conclusion. The conclusion that we have is correct. I just think for foundation, this is important. We said the projection of A vector onto B vector is of size 0 if there's a 90-degree angle between A vector and B vector. A vector projects onto B vector, its shadow is 0 big. 0 times anything is 0. A vector dot B vector, A vector dot B vector is AB cosine theta. Cosine of 90 degrees is 0, and this also works. You do get 0. Absolutely it works. What does that mean? Well, if it works, it always works, is what I mean. Absolutely it works. In fact, let me get rid of the 0 because it absolutely works always. But you're also, when you get it to be 0, it's orthogonal. That's hugely important. Did we draw the right conclusions in the earlier videos and earlier documents that were handed out? Of course we did. Of course we did. I just made the assumption that it was true, and I figured, it's okay, it is true. It's not a problem, but let's prove it. Let's prove it. That's why I wanted to come back a little bit and prove it a little bit. But this is across the board. How would this play out? I mean, I don't want to beat this thing up completely, guys, but let me just kind of let me make this maybe easy. Remember we talked about the other situation. You'll see what I mean in a second here, guys. Maybe I can kill a couple birds with one stone, so to speak. You got A vector here. Here we go again. You got B vector here. They're starting to look familiar, right? And then we said this right here, that was A vector minus B vector. Wow. The same exact argument's going to take place, ladies and gentlemen. It's going to be the magnitude of this guy, A vector minus B vector, its magnitude squared is going to, and wow, it's kind of, the interesting thing is it's the exact same guys on the right that we had last time. What's going on here? Yeah, we did this and we figured out that it was going to be A vector. Let me just kind of give you a short, this is A vector minus B vector. You can see it with the notes in more detail, guys. This is where the notes are better. I mean, it's like you don't have to deliver the same speech. You can look at it at your own speed. But A vector minus B vector, the quantity A vector minus B vector dot the quantity A vector minus B vector is, well, what's this guy? He's AX squared, AY squared, AZ squared. This is looking awfully familiar. The other guy is BX squared, BY squared, BZ squared. Okay, yeah, we've delivered that speech already. What's going on with this dot product? It's gonna be, well, how's it gonna be? It's gonna be the I hat, the J hat, the K hat. What's the I hat? It's gonna be AX minus BX. It's gonna be AX minus BX I hat, the quantity AX minus BX I hat, plus the quantity AY minus BY J hat, plus the quantity AZ minus BZ K hat. Dot, the same thing. Dot the whole big quantity AX minus BX I hat, plus AY minus BY, the quantity J hat, plus AZ minus BZ, the quantity K hat. When you dot them, you're going to get the quantity AX minus BX squared, the quantity AY minus BY squared, the quantity AZ minus BZ squared. Wait a minute. For that case, you're seeing it right, guys. Forgive me, guys. Let me just make sure this thing is okay. Hold on. You know where I'm going. You know where I'm going. Yes. You know what that means? Everything's the same, except this is a minus. This is a minus. And that's a minus. A minus or plus a negative, however you want, plus a negative, plus a negative, plus a negative. AX squared, forgive me, AX squared, AY squared, AZ squared. Subtract the sum. AX squared, subtract the sum, AX squared plus AY squared plus AZ squared on each side. So AX squared, AY squared, AZ squared goes. ax squared, ay squared, az squared goes. Done. Subtract the sum, bx squared plus by squared plus bz squared on each side. Those all go and these go. It's equal to 0. What's left? You know what you're looking at. You're looking at the same thing basically, guys. At that point, it's this. It's this. It's this. It's this. Divide by -2 on each side and you get this. And it's set equal to 0. Same kind of argument, guys. And I got it a little more. I got more detail. There's a number of ways you can do it. I think you'll like the notes. I think the notes are pretty straightforward when we're talking about that. And that's where it's going. And we did it in both. And like I said, with the notes, it was, I just think it's easier. In short, in all possible circumstances, in three-dimensional space, there it is, always. Always the case. Always. In three-dimensional space, it's always going to be the case. And that confirms all of the foundation that we assumed to have all along. All along we assumed this foundation, and it helped us with the cross product. And that confirms all of the foundation that we assumed to have all along, and helps us immensely with all of our prior conclusions with the dot product and cross product. Everything we did with the dot product and cross product earlier, it helps us immensely to do that. All right. Let me just say something just real quickly here, guys. Let me see what kind of time frame I'm talking about here. Okay. This is kind of a summary, a real fast just look at what I've said in the past. And shut it down, guys. Let me just go across and do it. Okay. Pretty important stuff. Again, I'm sure there's different ways to conclude this stuff, guys. To me, this is just a lot more intuitive. That's just my judgment. That's my opinion. Doesn't mean I'm right. I mean, it may not be the same for all people when they look at it. Everybody has their own opinion on these matters. But for me, it's a lot more intuitive. They'll go about it in some other ways, too. Some pretty fascinating conclusions. Beautiful conclusions on their own right. I mean, I cannot emphasize how great some of the mathematical literature is out there. Old and new. I mean, I've seen some of the older literature out there. I just think is amazing. So I draw reference to it quite a bit. Okay, let's let me say a couple things really quickly, talk about it, and kind of end this situation regarding this stuff, guys. Again, I believe those notes that you're going to see I believe the notes that you're going to see move a lot faster than the film does. You know what I mean? It's just the film is, and like I said, other people have given me that, agreed with the feedback that I'm kind of giving to you as well regarding that. It seems like the written notes, it's kind of odd how this whole crisis has kind of shown us. There's nothing like the old school being in front of people live where people can read one another's reactions and read one another, and you can ask questions live, and that human interaction, wow, it's something else. It does not get replaced by anything adequately, though the other things are wonderful as well, can help us quite a bit if we use them correctly, right? Technology is great when we use it correctly. But the in-person communication, it was great thousands of years ago, it's great now. And the notes that are written down are, if they're written down pretty decently, in a relatively strong fashion, they're as good as any film you're going to see on the topic, I think. So pretty fascinating stuff, I think. Regarding the cross product, guys, as we were able to conclude in earlier discussions, and I'll leave it more for the earlier discussions regarding that. we can say and again, it's, kind of we talked about, any A vector, and the A vector could be composed, the A vector could be composed of M vectors. The A vector can be composed of M as in mom vectors, and the B vector can be composed of N as in Nancy vectors. Any number of vectors is what A vector can be composed of regarding summing any number of vectors to get A vector. Regarding summing any number, a different number of vectors. Doesn't matter. They could be the same number of vectors, different number of vectors, doesn't matter. Any number of vectors summed together can give you A vector. Any number of vectors summed together can give you B vector. When you do their cross product, once you got that, we said it works. Like I said, when I showed you, I don't want to call it my way because I'm sure other people did this long before I did. The way I kind of showed it, where I don't really see it in many places, but I'm sure it's been done. Absolutely sure it's been done in other places. Just haven't run across it. I'm sure it's been done, guys. We say we can go like this. We draw that conclusion when we were saying, okay, can you find, like we just said, can we find a vector? It's always kind of in the back of our mind, man. We're saying like, the magnitude of A vector cross B vector is equal to the magnitude of the cross product. The magnitude of the cross product, A vector cross B vector, is magnitude of A times magnitude of B times the sine of theta. We talked about that. So just put that over to the side, times the sine of theta. Yeah, and we were able to find out how big that is in terms of the components of A and the components of B. I looked at the components of A vector and B vector, and we were able to derive what is the size of magnitude of A times magnitude of B times the sine of theta. The magnitude of A times the magnitude of A times the magnitude of B times the sine of theta. What is the size of that? We found that with the components of A vector and B vector. Then we said, okay, let's find the orientation. There's infinite number of vectors that have that size, A, B, sine theta. Infinite number of vectors have that size, A, B, sine theta. Yes, only two of them have that size and are perpendicular simultaneously to A vector and B vector. There is one vector perpendicular to both A vector and B. There's one vector perpendicular to both A vector and B vector in a right-handed manner, and there's one vector perpendicular to A vector and B vector in a left-handed manner. We only care about one of those. There's only two vectors that are perpendicular to both of those vectors simultaneously and have that sign. Only two vectors in the universe of vectors that satisfy that. Only one of them is right-handed, always. And the other one is always left-handed, always. I want the right-handed one. We played the games and we had to use the dot product to confirm what it have to look like. Give me some idea of what the dot product's got. Well, give me some idea of what the orthogonality conditions yield. And the dot product did it. We better have the dot product straight, and we do. Now we do, and then we did when we first did it. We assumed a lot, but we assumed right. Now we proved it. That dot product was right, the way it is. A vector dot B vector equals AX BX plus AY BY plus AZ BZ. Let's go. And then from there we took a couple good guesses. You had about 48 guesses you could make with the thing, man, that maybe would work. Maybe it didn't. I don't know. And we threw the dice and we got it. We concluded it. We knew what it was, and then we say, hey, you know what? That always fits into this. And then from there, you can put any number of vectors you want in there. I could take and put, all right, let me check, guys. I don't want to stop this. Okay, this thing's about to go. Let me change batteries, guys, in case this thing goes. Okay, give me 1 second, please. All right, guys, thank you for your patience here. Technology and I don't always get along, but okay. So we got this. I just wanted to make sure I had the recording audible for you guys, and we're looking pretty good. All right. But guys, I mean, the big thing here is you could plug in for a sub x all the components for this big a sub x. You could plug in all the x components of the following vectors: a sub 1 vector, a sub 2 vector, a sub 3 vector, a sub m vector. Those, how many are there? There could be a billion. There could be 10 billion of them. You could get all their x components, add them together, and that's your big a sub x vector. You could do the same exact thing with the 5 billion y components, add them together and get one big y component. Add them together, get one big x component for the x's. Same with the z's. Same thing happening with the x, the y, the z. If you did that, you could also leave them there and say, hey, let's stay with symbolism here. Let me stay with this guy, have m of these. Right here in this. Now, I already said, row 1, row 2, row 3. Row 1, row 2, row 3. Column 1, column 2, column 3. Never changes. It's a 3 by 3 determinant. I don't care if you put 5 billion vectors right here. Yeah, I can put them all the way across. The x's go across, the x, the y, the z. Here's your a1 vector. It's a1x, a1y, a1z, ... It's amx,amy, amz. There's m of them. There could be a billion of them. There's a billion vectors right here. Yeah, I know. You add them together, they form one vector. Same here. There's 10 billion vectors right here. Add them together, they form one vector. The components, write them in a column within a row, but make sure it's just one row, one row, one row. 3 rows, 3 columns. That never changes. And there it is. And basically you'd have m of these a sub I x's, m of these a sub I y's, m of these a sub I z's. Same here, you have n of these x's, n of these y's, n of these z's, sub something. And if you did this, if you actually played the thing out, it comes out to, like we said, let me just be extremely, it's a little different than how I finished it last time, but it doesn't matter. We finish it. And that comes out to everybody's going to get hit. You'll see in a second here. Everybody gets hit. It just gets hit in an awkward way, but they get hit. I hat plus a negative. Remember, we had to kind of do a guess with that to make it work, at least for one of the approaches. And again, Munham and Follis confirmed everything I said. I'm sure that other people said. And then I'm sure what I said and what other people said absolutely confirmed what Munham and Follis said. So Munham and Follis helped us a lot with this, and it verified, it went along the lines upon, in the ways that we were moving. We got this. AXBY. let's see what we got here. AX, BY, AY, BX. Yeah, it's out there. Now, true. Absolutely true. We've said this, I think, many times by now. It's true every time, guys. It's always going to be true. The thing is, if you had those, if you made these into megavectors here, all M of these, all M components, there's going to be M components with the A's, with the AYs, N as in Nancy component. So M is in mom and N is in Nancy components. M is in mom, N is in Nancy. M is in mom, N is in Nancy, all like this. The combinations that occur with M, with a polynomial, with a product of two polynomials, one of the polynomials has M terms in it, as M is in mom terms, and the other one has N as in Nancy terms in it. The number of combinations is M times N. And that'll happen here. You'll end up getting this vector. It's one big megavector. If you already summed them together, man, you made your life easy. There's your answer and you're done. If you want to make them in bits and pieces, you're going to have vectors looking just like this, but there's going to be M times N of them. We said there was a billion of them here, hypothetically, 10 billion of them there. Wow, really? Okay, a billion. Huh? A billion's 10 to the 9th. 10 billion is 10 times 10 to the 9th, which is 10 to the 10th. 10 to the 9th times 10 to the 10th, 10 to the 19, 10 to the 19 determinants. 10 to the 19 vectors, each one looking like this, sort of, right? That format at least. 10 to the 19th of them. However many you want to do, a trillion by a trillion. A quadrillion by a quadrillion. Well, who cares? You get the point. And that's what they're trying to say there. That's kind of where it's going. And that's where, you're looking at it, you could say, okay, and that, there's so many ways to go here, guys. Let me, this is all equal. Forgive, how I'm doing it here, guys. I think you understand here. And this is just on the side, tell us how big the vector is. How big is the vector? How big is the vector and how we talked about it? Now, we got this equals that, equals all that, equals this. Remember I said there was a billion of them by, the M, there was a billion. I mean, I don't know, I'm exaggerating here, but it's not exaggerating. I mean, theoretically it could be. A sub 1, A sub M is a billion of them. Cross. B1 vector plus equals this. What's that? Well, that's the sum of M times N of these. Let me see here. A sub I. Somebody between one. There's a billion of these. I is somewhere between 1 and a billion, including a billion and including 1. It could be any one of those. If some of these, all the different ways, and here the I's, you guys, the I right here and the J right here is not this. It's not K hat, J hat, I hat. I hat, J hat, K hat has nothing to do. This is just the index of summation. All of these, how many are there? M times N of them. M times N of them. It looked like this. It looked, I'm trying to write here, guys. This, try to write large enough so you don't have any issues here, guys. The summation of all, now these are really I hat. This is J hat, and this is K hat, absolutely. The I's right here are AIX, AIY, AIZ. AIX, AIY, AIZ. If you can't see it good, guys, I got it in the notes. Oh, that's the same I here. Oh, yeah, it's from this guy. Hypothetically, this general vector, A sub I vector. A sub I vector is composed of A sub I x. A sub I vector is A sub I x I hat plus A sub I y j hat plus A sub I z k hat. B sub j vector is B sub j vector is B sub j B sub j vector is B sub j x I hat, B sub j y j hat, B sub k, forgive me guys, let me just write it again. Okay. B sub j vector is B sub j x I hat plus B sub j y j hat plus B sub j z k hat. The I and the j are nothing to do, the I and the j are nothing to do with I hat and j hat and k hat. The A sub I vector is A sub I x I hat plus A sub I y j hat plus A sub I z k hat. The B sub j vector is B sub j x I hat plus B sub j y j hat plus B sub j z k hat. That's how it goes. How many are there? M times n. M times n. Hopefully that's large. I try to make it as large as I can. I know that the writing gets a little more, is more legible toward the middle of the board, you guys. But I do have this in the notes, and it's at the end of the notes. I added some other stuff here and some other stuff I did not put in there. But that's some of the argument that takes place. And pretty fascinating conclusions. I mean, in totality, the videos should get us to where we want to go. I don't know how many videos there were. I think there were 2, and then this one 3, and then there's four handouts. So something on the order of 3 videos and 4 handouts associated with them. At the end of this video, you'll have all 4 of the handouts put together. Okay. All right, guys. Thank you so much for your time. Take care. Good luck to you in all that you do. Bye now.